his introduction, and that's very true. I also remember meeting you a long time ago on this Polariton workshop. I want to thank Dimitri and Guillaume as well, because putting together this conference in this very particular situation is far from simple, and I think they really did a good job. So I'm going to talk now of a slightly different topic. So we are going to discuss about quite different material. So that's monolayer materials, semiconductors, MoSe2 in particular. And I'm going to show you our recent results in which we have been interested in exciton-exciton interaction in such new kinds of semiconductor materials and what we could do with that in microcavities. So I don't need to insist much on the idea that a large chi-3 nonlinearity is something very interesting and very useful in the context of application in quantum optics. Basically, let me put a pointer. Basically, what we're interested in this kind of setup here, where we want to control a target state, which is a quantum state, with a control state. We would like this control state to be as quantum as possible, so like a single photon. And so for that, we need to have a chi-3 which is as large as possible. And this is currently a very strong quest, trying to increase this chi-3 as much as possible. So excitons are great for that. They have a great potential to provide a large optical nonlinear chi-3, because they interact strongly with light and because they feature two-body interaction via two channels, Coulomb interaction, which is very well known, very much discussed, and a bit less discussed is the fermionic saturation due to the electron hole constituents of the exciton. So there are already many applications of excitonic nonlinearity. The most obvious one is excitons in quantum dots, where the chi-3 is basically the largest possible, thanks to the fermionic saturation, actually. But as it was pointed out already before, this is not straightforward to manipulate and to fabricate device out of these quantum dots. So the second option is to use quantum well inside microcavities and to try to use the remaining chi-3 nonlinearity of the exciton in heterostructures involving 2D exciton, let's say, in quantum well, or like I'm going to discuss in a monolayer semiconductor material. The thing is that it's in principle much easier and more flexible if we have in mind some application for quantum optics, like generating quantum light out of classical light. So of course, we have heard Thomas Volz yesterday showing that it was actually possible. It's hard, but possible to enter into the quantum regime of the nonlinearity. I was quite impressed by Paul Walker's talk as well, where he has shown something which is very similar to my little drawing here, with very few polaritons used to switch the gate. So this is an exciting topic. So I'm going to focus on the case of quantum well in microcavities, or at least of 2D excitons, for this reason that it's interesting and easier than quantum dots. So I wanted to make a quick reminder of how exciton-exciton interaction works in a 2D geometry like quantum wells. So there's been many theoretical derivations. This is the simplest one I'm showing here. So I know that there are some debates on whether it's quantitatively correct or not. We know that it's probably not quantitatively correct, sorry. But at least qualitatively, it's pretty accurate, I think. So the exciton-exciton interaction via the Coulomb term scales like the binding energy of the exciton and the Bohr radius. And if you have a wave function for the exciton, which is hydrogenic, this expression simplifies very much such that it depends only on the reduced mass of the exciton mu. If you do the same kind of approach for the saturation term, you find that the saturation term only depend on the relative permittivity of the material and this reduced mass. So basically, this very simple discussion shows that Gx and Gs, the nonlinear magnitude, are extremely stuck to the very intrinsic quantities of the material. Mu that comes from the electron on hole effective mass is something very hard to change. So you're not going to be able to engineer Gx simply. Same thing for epsilon r. It's a quantity which is very intrinsic to the material, so it's hard to tune. So what happens when you are dealing with a hydrogenic wave function, which is the case of most classical conventional semiconductor material, you are stuck on this line here, where here what I'm plotting is Gx versus the reduced mass, actually not effective mass, mu. And you see that you have this, this nice alignment of the material, where when you have a small band gap material, you have a large Coulomb interaction. And when you are in the high band gap material, you have a small g. And with the advantage here that you can go to room temperature, but you have a vanishing interaction term, basically. So you are a little bit stuck in this trade-off when you are dealing with a conventional material where the wave function is hydrogenic. So what is very interesting with TMD material, so transition metal decalcogenide, so that's a semiconductor of atomic scale thickness, you are dealing with an exciton in which the Bohr radius is larger than the thickness of the material. And just because of that, the Coulomb interaction between electron and hole is heavily modified. You are not dealing anymore with the 1/r potential, but something like log of r. And in this situation, the excitonic wave function is not hydrogenic anymore. It has a different shape in space. And so this has been already pointed out in several experiments. For example, this nice one here in 2014, where you see that the series of excited states do not follow at all the 2D hydrogen model, but there is a strong departure from it. So, of course, this shape of the wave function is expected to change the value of Gx and Gs. And actually, it was shown in 2017 is in this very nice paper by Shelik and Kirienko, that the Gx can be actually increased by as much as 35% as compared to a comparable material with respect to a comparable material. And this is a calculation explicitly done for WS2. And we don't know actually what's going on for GS. We expect GS to change as well, because GS depends, of course, very much on the shape of the wave function. So starting from here, we wanted to measure Gx and Gs in a TMD material inside a microcavity in the strong coupling regime, because it makes it very convenient to measure accurately Gx and Gs for this kind of material. We are dealing here with MoSe2 in this case. So this is what the structure looks like. This is an optical micrograph. So this triangular shape here is actually the top mirror of the microcavity. The light gray one is the bottom mirror, and the red section here is actually an MoSe2 monolayer, which is sandwiched between the two mirrors. And here you have a quite good planar microcavity with a monolayer of MoSe2 in the middle. This is what the cross section looks like. And this is a structure that has been fabricated in Würzburg University under the direction of Christian Schneider. This is quite an impressive thing to fabricate, because of course you want your cavity mode to be resonant with the excitonic transition of your MoSe2 layer. So this is really not simple. So a quick characterization of this microcavity. So we did measurement at this particular point here. And what we did is we changed temperature to change the excitonic energy and to obtain an anti-crossing behavior of the two polariton modes. And you see this anti-crossing here, the upper polariton, the lower polariton here. And you can fit that with a two-coupled oscillator model, and you find a Rabi splitting of about 25 MeV. which is quite striking when you realize that it's a single monolayer of material that's inside. It's a huge oscillator strength. Okay, so we know where we are. We can choose our temperature, like 130 K, for example, to work at a position where we have a good mixing of exciton and photon in our polariton states. And now we are going to measure the nonlinearity of this system. And to do that, we do the following experiment. We have a beam splitter here, a pulse laser, 200 femtosecond pulses. We have one pulse that goes through across the sample, and we measure the transmitted light intensity inside a spectrometer, intensity and spectrum. And we have a reference beam that also enters the spectrometer on a different position of the CCD, so that we have two spectra, one that is transmitted and one that is the reference pulse, such that we can calculate the time average transmission spectrum of the system. So this is what we obtain here, a typical measurement of what we obtain as a transmission spectra, in this case at 105K, where we are a little bit photonic, and versus power, so the pulse energy here in picojoules. So here we are in the linear regime. We have a lower polariton peak. We have an upper polariton peak that's a little bit faint here to see. And you see that upon increasing the pulse energy, we have a small blue shift as expected due to the interactions. Now we change to another detuning where we are a little bit more excitonic, and we do the same experiment, and we see that we have a much stronger blue shift here on the lower polariton and something like a flat and slight red shift for the upper polariton here that we observe in this series of spectra. Okay, so if we want to make sense of this measurement, in particular quantitatively, we have to go through an accurate theoretical description of what is going on in the experiment. In particular, because we are measuring time-integrated quantities, so it's not straightforward to interpret. So we have actually derived mean field equation describing the system. And it's not so straightforward because we have upper and lower polariton in this case. We have the saturation interaction and the Coulomb interaction that we want to take into account. And we need to take the spin degree of freedom, so the polarization, into account because we have a well-defined polarization state for the pump. So the Hamiltonian of the system is very usual in the exciton-photon basis. This is the linear part. And we have the two Coulomb parts of the interaction here. So the one when the spin are parallel, the one when the spin are perpendicular, and we have the saturation term. So we have three nonlinear terms in this Hamiltonian. And the sigma here is the spin states of the field that are involved in the circular basis. Okay, so we derive the equation of motion. We take the mean field approximation and use the input-output theory to include the drive and the dissipation. And we obtain these two mean field equation. That's a little bit heavy, but actually it's the usual one, nearly. So we have the pump and the losses as usual. We have the Coulomb interaction, which is very much as usual as well. What is a little bit different is that you see that the saturation in the exciton-photon basis appear in three different terms. In particular, we were quite surprised to find this term here, where the phases of the relative field matters. And we verified that it's actually important to take into account. And so with that, we take every degrees of freedom that we need to understand what we are doing. So what we do is we integrate numerically this equation, taking into account the shape in space and time of the pump. We time integrate numerically the results, and we see what spectrum we get. And so we do that. These are the same spectra that I've shown before, but not in color plot, like in a more accurate way. And the gray lines here is a fit with this theory that I've just shown. You see that we obtain quite a good fit everywhere, whatever the detuning here and the power. And here the red dotted line is actually where the spectrum of the pulse. Okay, so we do a real fit in the sense that we do an optimization such that we can derive really the GX and the GS that match our experiment, and we obtain these two quantities. In this case, we obtain a sum of GX parallel and perpendicular because we have done the measurements with linear polarization. Okay, so if we come back to this, the conventional material that I've shown at the beginning, we wanted to compare with these values in a quantitative way. So like I said, we are not very confident with the pre-factor that we have in the theory. You probably remember this factor of 6 in Cristiano's theory. So in order to get rid of that, we used an experiment actually to scale the theory. So we used this recent measurement that was done recently in Australia. That was done quite accurately, and in particular, it was done in a planar cavity with not too much reservoir around, and they have been very careful in trying to determine quantitatively the value of their GX. So we used this quantity to scale this theory here of the interaction in the conventional material, and we could put our measurements on this chart. And we see that we are a little bit above, but considering the error bar, we can see that there is possibly a slight enhancement, but it is within the error bar. Interestingly, we see that we are very consistent with what has been derived quantitatively in this work. Okay, so we did the same thing for GS, using also this experimental data to scale the theory. And we see that in this particular case, we are far above the theory. We can zoom in a little bit, and actually, if you put numbers, we are 7 times larger than we should be for an exciton with an equal Bohr radius in a conventional material, in a conventional semiconductor, if you want. So this was quite a surprise, and we were very interested by this feature. So I would like to finish this talk. I would like to give you a very hand-waving argument for why we have this 7-fold enhancement of GS, possibly. So like, if you remember, GX for the Coulomb interaction basically scales like the Coulomb potential at the position of the Bohr radius. So this depends on the particular Coulomb potential that you use. So it's not the same for extreme 2D like in TMDs and in quantum well. And you have a square of the Bohr radius, which would be rather considered as a length scale of the size of the wave function. And in fact, so these two terms have a tendency to cancel each other, because this is more or less equal to the kinetic energy of the carriers, the average kinetic of the carriers in the wave function. And this goes like 1 over mu, 1 over AB square, sorry, times mu. And in the end, these two quantities cancel each other such that we have only 1 over mu. So this is true for the hydrogenic wave function, but this is also at least qualitatively true for a distorted wave function due to a change in the details of the Coulomb potential. If we investigate GS, obviously you don't have the potential that appears explicitly, but you still have this factor of AB square that appears in GS, because you have this overlap integral that involves the wave function of the exciton. And AB is the characteristic size of the wave function of the exciton. And of course, this this characteristic size is the result of the solution of the problem when you try to solve the excitonic problem in this new Coulomb potential. So here, what happens is that although you don't have explicitly V that appears in this expression, GS seems to be actually more sensitive to the details of the Coulomb potential than GX.
1 minute.
So, sorry?
You have 1 minute.
Right? 1 minute, perfect. So it's actually a bit striking to see that, and I think we are quite convinced of this argument. But of course, it would be extremely interesting to have some accurate theoretical derivation of this effect of this argument. Okay, so with that, I'm going to conclude. I would like to acknowledge my coworkers, in particular Peter Stepanov, who did a fantastic work in the experimental part, and Amit Vashisht, who did all the theoretical derivation and who did really a fantastic job because it was not easy. He's working with Anami Gudzi in LPMMC, with whom we are working very closely. And this project has benefited a lot from, well, the sample, obviously, and also from physical discussion with Christian Schneider and others, Thomas Foltz in particular, and Christian, who is at Würzburg and now at Oldenburg. And with that, I'm finishing. Thank you very much for your attention.
Thank you, Maxime. Merci. The talk is open for questions. I don't see any question right now. So while you think, it's always been a messy and highly debated problem, this question of interactions. We have talked this morning.
Yes.
It's a long time. So what is your opinion? Is the situation getting more and more clear and we are reaching a consensus, or with time it's even more and more debated and controversial?
I think it's getting a little bit clearer over time. So first, an important point is that people have realized the past 3, 4, 5 years that you have to take into account an incoherent reservoir that bias the measurement of GX. And when you take that into account, things seem to be a bit easier to interpret. So the numbers start to converge a little bit better, the experimental numbers at least. So I have the impression that things are getting a little bit clearer. I think the difficulty is more on the material aspect than on the theory. The materials, the excitonic part, the exciton state in the material, let's say, is not straightforward because there can be disorder, etc. So this would need to be taken into account, I think.
Okay. Let's have people speak. Thierry Guillet has a question.
Yes, sure. Thank you, Maxime, for the nice talk. In the case of TMDs, you can have an asymmetric dielectric environment with a thick HBN layer bottom and a thinner on the top. Can you see how it impacts the interaction between excitons if you have an asymmetry on the dielectric environment?
Yeah, it's a great question. So you are absolutely right. And in fact, it's one of the interesting aspects of TMDs. It's the fact that you are basically on a surface. And so you're actually the exciton, even the exciton has a wave function that goes outside the material. So indeed, when you put any dielectric environment around the monolayer, you are going to change completely the properties. So that includes the Bohr radius, which in turn will affect GX and GS, but also GX and GS themselves via the Coulomb interaction, because the Coulomb interaction is also going to change.
Okay, thanks. Tanli Bing has a question.
Hi, hello. So I understand that your measurements don't have time resolution, right? So
yes.
Yeah, so we also did, so here in Imabel Blue group in ETH Zurich, we also did similar measurements. And we see that there can be, especially when you populate also the upper polariton state, for example, you can have a pretty significant reservoir population that can accumulate, and this could cause a blue shift even well after the coherent polariton lifetime. So could you comment on why this might not be important here? Also that from the group of Kenna Cohen in Montreal, I believe that they measured interaction strength that was of 6 × 10⁻² micro EV micrometer square, which deviates quite a bit from, I think, what you guys found.
Maxime, because we have other questions.
Sorry. Yeah, yes. Yeah, it's a very good question. So of course there can be, so we looked into that in detail actually. I can show you briefly one slide. So it's true that in this theory, we didn't assume any long-lived reservoir in the system, simply because we didn't see any at the moment. So I can show you briefly this. We did some time result measurement afterwards, and this is what you see in panel C, for example. What we have seen is that we couldn't see any long time delay component into the decay, which means that the photons that we get all come from polaritons without passing through a reservoir. Okay, so it doesn't mean that there is no reservoir. It just means that it has probably a terrible quantum yield, a very low one, which means also that when you have a very poor quantum yield, you have a reservoir that cannot accumulate excitations. And so it will not contribute very much to the interactions. But it's very much sample dependent. That's the hard part. It's very hard to compare from one group to another because it depends completely on what you have around your monolayer. If it's HBN, if it's PMMA or whatever, you can have, I guess, a completely different situation in terms of this possible reservoir.
Okay, thank you. And given the talk he gave this morning, I'm sure it will be very interesting question from Olivier Bleu, but quick, please.
Hi, Maxime. Thank you very much for your talk.
Hi,
yes, I have a question about the singlet interaction because for polariton with opposite spin. And because, in fact, because of the existence of the bi-exciton resonance, as I have shown this morning, you can have, in principle, especially in monolayer system, you can have signature of an enhancement of this singlet interaction, and this is not the case in the experimental paper from Australia, because it has been done in a multi-layer cavity, and in such type of system, alpha 2 or the singlet interaction for polaritons should be very small and is negligible. So what they measure is only the triplet interaction. So could you comment on this?
Absolutely. And in fact, if you look at the panel on the right of this slide that I've not shown, we have measured the blue shift versus the state of the incoming, the polarization state of the pump. And it's actually very striking because what we see is that if we go co-polarized, we have a lower blue shift than when we are linearly polarized. And if you put numbers into that, it means that the singlet channel is actually larger than the triplet channel. And it is very puzzling. And one of the hypotheses that we have proposed is indeed exactly what you said, that we might be enhanced by the bi-exciton transition, which is very close to where the lower polariton is. But okay, we need to check that. We need to check that carefully because there can be other explanation. But we observe exactly what you say.
Yeah, it looks very interesting.
We have to stop the talk here because we are really running a lot out of time. Next talk will be